So we are doing chapter number 20, permutations. So in the previous lecture, we have defined that permutation is a bijective function. And then we have defined some properties. And then we have defined that how these permutations behave is a bijective function. Then we have said that the number of permutations for the set which has n elements is n factorial. We have proved that, and we have gave some examples. Then we have talked about how we can permute the like how we can compose the permutations. We have given the definition, and then we have defined it by having some examples. Then we have said in the end that permutation satisfies some particular properties, and those properties are that permutations are closure. So if you take two permutations and compose them, you will again find a permutation, and the permutations follows the associative property under composition. And there is always an identity permutation in a set for a set, and then you will always find a unique inverse in for every permutation in the set of permutations for a particular set. And we have proved that. Now we are going to talk about how we define the permutations in a different notation, and we use the cycle notation for that. So the topic is going to be cycle notation. So the notation at this time we are using is, so let's say we have a permutation. Let's say the notation we are using this notation at this time, that we are saying we have 1, 2 up to n, and for that we are saying that we have f of 1, f of 2 up to f of n. Okay, and so the notation for permutations is rather cumbersome and is not particularly convenient for performing calculations. Okay, so there's much more compact and useful notation, the cycle notation for permutations, which I will now describe. So let's say, consider the following permutation in a set. The following permutation in S8, the set which has 8 elements, and then Sn stores all those permutations in for that set. And that permutation is that F can be written as 1, 2, 3, 4, 5, 6, 7, 8. And we are sending 1 to 4, 2 to 5, 3 to 6, 4 to 3, 5 to 2, 6 to 7, 7 to 1, and we are fixing 8. Okay? And now this sends. So you can also write this. You can say this sends. This sends 1 to 4, 4 to 3. Okay? And then 3 to 6, then 6 to 7, right? And we are back to 1 is 7 sends 7 goes to 1. So we say that the symbols 1, 4, 3, 6, 7 form a cycle of length 5. Similarly, we send 2 and 5 form a cycle of length 2 because we send 2 to 5 and 5 to 2. So 2 and 5 form a cycle of length 2, and we send 8 to 8. So it's form a cycle of length 1. So it forms a cycle of length 1. We then write that F is nothing but cycle, which is 1, 4, 3, 6, 7, 2, 5, and 8. So if you look thoroughly to this cycle, you will find out that we send 1 to 4, 4 to 3. So if I can explain it more, 1 to 4, 4 to 3, 3 to 6, and 7, 6 to 7, and then we are back from 7 to 1. Something like 2 to 5, and then 5 to 2, then we have a loop on 8. Something like that. So it is fixed. This is how we say that at is fixed. Okay. Now the notation indicates that each number 1, 4, 3, 6, 7 in the first cycle goes to the next one, except for the last, which goes back to the first, and likewise for the second and third. This is the cycle notation for F. So we say that this is a cycle notation for F. Now notice that the cycles have no symbols in common. They are called disjoint cycles. So you can say, notice that the cycles have no symbols in common. So we call them that they are disjoint cycles. Now it is easy to move back from the cycle notation to the original notation if desired. So for example, if G is a cycle which is 1, 3, 7, 2, and 4, 6, and 5 is fixed in S7, then the original notation for G is we have 1, 2, 3, 4, 5, 6, 7. Now we are sending 1 to 3, then we are sending 3 to 7, then we are sending 7 to 2, and then we are sending 2 back to 1. Okay, and then now we are sending 4 to 6 and 6 to 4, and we are keeping 5 fixed. So this is how we can get back to the original notation from a cycle notation. Okay, now let's say every permutation, hey, every permutation in the set Sn can be expressed in cycle notation. Cycle notation. Here is the procedure for doing this. So let's say we begin with 1 and write down the sequence until we reach 1 again. So begin with 1 and write down the sequence 1, f of 1, f of 2, sorry, f of 1, f square of 1 until we reach 1 again. Now this must happen since we are working with the finite state. So we cannot carry on writing down new symbols forever. Okay, now say f of r, if power r of 1 is 1, then r symbols for 1, f of 1, square of 1 up to f power r of 1 or minus 1 form the first cycle of f. Form the first cycle of f. To get the second cycle, to get the second cycle, choose a symbol not appearing in the first cycle. Okay. And call it I. Then repeat the above process. Okay. Repeat the above process. Write down the sequence. So write down the sequence, which is I, f of I, f square of I, f square of I, and so on until we reach I again. And say that f of s, f power of s of I is I again. Then there are no then we have the sequence I, f of I, f square of I up to f power s of I is the second cycle. Is the second cycle of f. Now carry on this process until there are no symbols left. Carry on this process until there are no symbols left. We get the cycle notation for f. Right? Now, the cycle we obtained have no symbols in common, so we call them disjoint cycles. So to summarize, let's give a proposition. We call it 20.3. We say that every permutation in the set Sn can be expressed as a product of disjoint cycles. And we have just proved it. Just proved this proposition by the above paragraph. Now the expression for permutation in cycle notation is not quite unique. First, each cycle can begin with any one of its symbols. For example, So you can have, you can say expression for a permutation in cycle notation is not unique. It's not unique, which means we can begin with any symbol to begin a cycle. So let's say the cycle the cycle 1 3 2 7 5 has exactly the same effect on each of its symbols is the cycle 3 2 7 5 1. So you can say they are equivalent. The second is the order in which we write the disjoint cycles does not matter. So if I have to say that the order in which we write the disjoint cycles does not matter. So for example, you can write 1 2 4 and 3 5 3 5 is the same permutation as is same as 3 5 1 2 4. But be aware, it is only for disjoint cycles. It is only true for disjoint cycles. Okay. So in the non-disjoint cycles, it is not true. So you can say that 1 2 3 2 4 is not equal to 2 4 1 2 3. Okay, perfect. Apart from these two ways of changing the cycles, the cycle notation for a permutation is unique. So, for example, the only ways of expressing the permutation 1 2 4 3 5 in S5 as a product of disjoint cycles are. So, we can give an example now. So, example, whatever we said. So, late F is a permutation in the cycle notation. In S6 and G is a permutation in the cycle notation and S6 also. Then the composition of F and G, or the multiplication of F and G, is nothing but 1, 5, 4, 5, 2, 6, and 3 is fixed. So how you do that? So to do that, what you have to see is you first write so here's what I said to myself to do that. So let's say start with 1. 1. Now G sends 1 to 6 and F sends 6 to 4. So FG will send, or just sends, 1 to 4. Then it sends 4 to 5. Then 5 to 1. Now how it sends 4 to 5? Because G sends 4 to 2, and F sends 2 to 5. So FG sends 4 to 5. Similarly, G sends 5 to 5, and F sends 5 to 1. So FG sends 5 to 1. Okay, this is somehow we can do that. And so the first cycle of, you can say, so the first cycle of FG is 1, 4, 5. Now look at 2, because after 1 we have 2, so which is not in this cycle. Which is not in 1, 4, 5. So FG sends 2 to 6 and 6 to 2. Then 6 to 2. So 2, 6 is the next cycle. Now how FG sends 2 to 6? So see that G sends 2 to 4, and then F sends 4 to 6. So FG sends 2 to 6, and then G sends 6 to 3, and F sends 3 to 2. So that's how FG sends 6 back to 2. Okay, then if you look these 2 cycles, the only remaining number is 3. So finally FG sends 3 to 3. So 3 is the last cycle. Now how FG sends 3 to 3? G sends 3 to 1, and F sends 1 to 3. So FG sends 3 to 3. Now, the other way of doing this is again simple. If you want to multiply fg, the like this could be the most lengthiest way in doing in mind. So what you need to do is you are writing fg. You want to write fg. So write f, which is 1, 3, 2, 5, and 4, 6, and then write g, which is 2, 4, 1, 6, 3, and 5. Okay. Now check. You want to decide about 1. So you want to see 1 is going to 6. So 1 is going to 6. And then you leave this whole cycle of G, cycles of G, and look that in these two cycles. So F in this cycle, 6 is going to 4. So that means you are getting 1 to 4. Now you are at 4 in the FG cycle. Now look that 4 into G, where it is going? It is going back to 2. And then see that in these first two cycles, where 2 is going. So 2 is apparently going to 5. So the next element would be, symbol will be 5. Now we don't know whether we need to close it or not. So now we will look where 5 is going in G, but 5 is going back to itself. So 5, G sends 5 to 5. Now you need to look in the F cycles that where is 5 going? So 5 is going back to 1. That means we can close this cycle, because if we close this cycle here, then we will get back, 5 will get back to 1. So we can close this cycle here. Perfect. Now we will check now that there is 1 there, but there is not 2 in this cycle. So what we do, we will look for 2 in last 3 cycles, which are for G. So we will see that 2 is going to 4. So 2 is going to 4 in here, but like 4 is going to 6 now. That means 2 is going to 6. Now then we will see that 6 is going to 3, but 3 is going to 2. It means we can close this cycle. Perfect. Similarly, the remaining element would be 3. Now we will write 3 and see where is 3 going. So in this one, 3 is going here, and then 1 is going back to 3. So we will close this cycle, and that's how we get 1, 4, 5, 2, 6, 3. This is another way of doing that, above one or the below one. Okay, that's how we multiply the cycles. Okay. Now, if G is a permutation given in cycle notation, the cycle shape of G is the sequence of numbers we get by writing down the length of the disjoint cycles of G in decreasing order. So let's write that. If G is an Sn is a permutation given in cycle notation, the cycle shape of G is the sequence of numbers we get by writing down the lengths of the disjoint cycles of G in decreasing order. Okay. So for example, the cycle shape of the permutation permutation 1 6 3 2 4 5 8 7 9 in the set of permutations over the set 9 elements is nothing but 3 2 2 1 1. Normally we write that we collect the repeating numbers and write this more concretely. So normally we collect the repeated numbers and write this more secondly as 3 2 square 1 square. Now let's give the example. So number 1, how many permutations of the cycle shape 2 comma n power minus 1 1 power n minus 2 are there in Sn? Okay, so the question is how many permutations of cycle shape 2 comma 1 power n minus 2 are there in the set Sn? To answer this, now this is easy. So it is just the number of choices of a pair 1 comma I to make 2 cycle. So it is just a number of choices of a pair I comma j to make as 2 cycle, make a 2 cycle which is n choose 2. Perfect. Number 2 is how many permutations of a cycle shape 3 2 square 1 are there in Sn? So let's ask how many permutations of cycle shape 3 2 square 1 are there in the set Sn. So this is slightly more tricky. Now, for what we need to do, first we have to choose 3 symbols. First, we have to choose 3 symbols I, J, K to put in a 3 cycle. And given ijk, we can make 2 distant 3 cycles. Those are I, J, K and I, K, J. Or you can write without any commas, I, J, K and I, K, J. There are 8 compose 2, 8 choose 3 multiply 2 choices for a 3 cycle. Cycle. Next, we choose 2 symbols L, M from the remaining 5 to put in the first 2 cycle. From the remaining 5 to put, because if you have 3 cycles, then we are looking into asset, then we are remaining with 5 more symbols. So 5 remaining from the remaining 5 to put in the first 2 cycles. Cycle. Then 2 more. 2 more, which is N, O, to put in the this gives 5 choose 3, 2 multiply 3 choose 2 choices. But we must divide this number by 2. Since LM and O is N is NOLM. Hence, the number of permutations of cycle shape 3 2 square 1 is 8 choose 3 multiply 2 multiply 5 choose 2 multiply 3 choose 2 multiply 1/2, and that is 1680. Very big number. Okay, perfect. And then we can talk about repeating a permutation in the next video.